The periodic table. There are over 100 chemical elements which have been isolated and identified. Each element has one proton more than the element preceding it. This is done so that elements end up in columns with other elements which have similar properties. Elements are arranged on the periodic table in order of increasing atomic number. The table is arranged in vertical columns called groups and in rows called periods. Period. These are the horizontal rows that show the number of shells of electrons an atom has and are numbered from 1 to 7. E.g. elements in period 2 have 2 electron shells, elements in period 3 have 3 electron shells. Group. These are the vertical columns that show how many outer electrons, also known as valency electrons, each atom has and are numbered from I7, with a final group called group 0 instead of group 8. E.g. Group 4 elements have atoms with 4 electrons in the outermost shell, group 6 elements have atoms with 6 electrons in the outermost shell, and so on. The group number can help determine the charge that metal and non-metal ions form. For metals, the group number corresponds to the number of electrons it will lose to achieve a full outer shell and the charge of the metal ion. E.g. sodium is in group 1, it will lose 1 electron and form an ion with a 1+ charge. Magnesium is in group 2, it will lose 2 electrons and form an ion with a 2+ charge. For non-metals in group 7 and V, they will gain 1 and 2 electrons respectively to gain a full outer shell. E.g. non-metals in group 7 gain 1 electron to form ions with a 1 charge. Non-metals in group 6 gain 2 electrons to form ions with a 2 charge. All elements are arranged in the order of increasing atomic number from left to right. Valency. Valency, or combining power, tells you how many bonds an atom can make with another atom or how many electrons its atoms lose, gain or share, to form a compound. E.g. carbon has a valency of 4 as it is in group 4, so a single carbon atom can share 4 electrons to make 4 single bonds or 2 double bonds. The following valencies apply to elements in each group. Exam tip. An easier way of remembering which number is the mass number and which is the atomic is: mass number equals the massive number, i.e. the larger of the two numbers. The atomic number must be the smaller number. The metallic character of elements. The metallic character of the elements decreases as you move across a period on the periodic table, from left to right, and it increases as you move down a group. This trend occurs due to atoms more readily accepting electrons to fill their valence shells rather than losing them to have the previous, already full, electron shell as their outer shell. Metals occur on the left-hand side of the periodic table and nonmetals on the right-hand side. Between the metals and the nonmetals lie the elements which display some properties of both. These elements are referred to as metalloids or semimetals. Properties of metals and nonmetals. A zigzag line in this diagram separates the metals on the left from the nonmetals on the right. Periodic trends and electronic configuration. The electronic configuration is the arrangement of electrons into shells for an atom, e.g., the electronic configuration of carbon is 2, 4. There is a link between the electronic configuration of the elements and their position on the periodic table. The number of notations in the electronic configuration will show the number of occupied shells of electrons the atom has, showing the period. The last notation shows the number of outer electrons the atom has, showing the group number. Example: electronic configuration of chlorine. The electronic configuration of chlorine is it should be written. Period. The red numbers at the bottom show the number of notations, which is 3, showing that a chlorine atom has 3 shells of electrons. Group. The final notation, which is 7 in the example, shows that a chlorine atom has 7 outer electrons and is in group 7. The position of chlorine on the periodic table. Elements in the same group in the periodic table have similar chemical properties. When atoms collide and react, it is the outermost electrons that interact. The similarity in their chemical properties stems from having the same number of electrons in their outer shell. For example, both lithium and sodium are in group 1 and can react with elements in group 7 to form an ionic compound. Charges of group 1 ions are 1+, charges of group 7 ions are 1, by reacting in a similar manner and each donating 1 electron to the group 7 element. As you look down a group, a full shell of electrons is added to each subsequent element. Lithium's electronic configuration, 2, 1. Sodium's electronic configuration, 2, 8, 1. Potassium's electronic configuration, 2, 8, 8, 1. Exam tip. Electronic configurations can be shown with the numbers separated by commas or by full stops. In this course commas are used, but you will often see full stops used elsewhere. Both are accepted. Predicting properties. Because there are patterns in the way the elements are arranged on the periodic table, there are also patterns and trends in the chemical behavior of the elements and their physical properties. These trends and properties occur down groups and across the periods of the periodic table. As a result, we can use the periodic table to predict properties such as boiling point, melting point, density, reactivity. Some common properties, trends and properties include: Group 1 elements react very quickly with water. Noble gases are unreactive. Transition elements are denser than Group 1 elements. Reactivity decreases going down Group 7. Melting point decreases going down Group 1. In this way, the periodic table can be used to predict how a particular element will behave. Identifying trends. Extended. Using given information about elements, we can identify trends in properties. An example of when this might be used is to determine the trend in reactivity of Group 1 metals. The table below shows the reactions of the first 3 elements in Group 1 with water. Observations of lithium, sodium, and potassium with water. The observations show that reactivity of the Group 1 metals increases as you go down the group. Using this information, we can predict the trend going further down Group 1 for the elements rubidium, cesium and francium. As the reactivity of alkali metals increases down the group, rubidium, cesium and francium will react more vigorously with air and water than lithium, sodium and potassium. Lithium will be the least reactive metal in the group at the top, and francium will be the most reactive at the bottom. Francium is rare and radioactive, so is difficult to confirm predictions. Table to show the predicted reaction of other Group 1 elements with water. Exam tip. For the extended course, you may be asked to identify other trends in chemical or physical properties of Group 1 metals, given appropriate data. Firstly, ensure that the metals and associated data are written in either descending or ascending order according to their position in the group. Then look for general patterns in the data. Group 1 properties and trends, basics. The Group 1 metals. The Group 1 metals are also called the alkali metals as they form alkaline solutions with high pH values when reacted with water. Group 1 metals are lithium, sodium, potassium, rubidium, cesium and francium. They all contain just one electron in their outer shell. Physical properties of the Group 1 metals. The Group 1 metals are soft and easy to cut, getting even softer and denser as you move down the group. Sodium and potassium do not follow the trend in density. Have shiny silvery surfaces when freshly cut. Conduct heat and electricity. They all have low melting points and low densities compared to other metals, and the melting point decreases as you move down the group. Some would melt on a hot day. The alkali metals lie on the far left-hand side of the periodic table. Chemical properties of the Group 1 metals. They react readily with oxygen and water vapor in air, so they are stored under oil to stop them from reacting. Group 1 metals will react similarly with water, reacting vigorously to produce an alkaline metal hydroxide solution and hydrogen gas. The Group 1 metals get more reactive as you look down the group, so only the first 3 metals are allowed in schools for demonstrations. Reactions of the Group 1 metals and water. Predicting the properties of Group 1 elements. Knowing the reactions of elements at the top of the group allows you to predict the properties of other elements further down Group 1. Properties of other alkali metals: rubidium, cesium and francium. As the reactivity of alkali metals increases down the group, rubidium, cesium and francium will react more vigorously with air and water than lithium, sodium and potassium. Lithium will be the least reactive metal in the group at the top, and francium will be the most reactive at the bottom. Francium is rare and radioactive, so is difficult to confirm predictions. For example, the reactions with water can be predicted. Predicting the reaction with water. You can also look at other properties such as boiling point, melting point and density of group 1 elements and use them to predict whether the other properties are likely to be larger or smaller going down the group. Group 7 properties and trends. The halogens. These are the group 7 nonmetals that are poisonous and include fluorine, chlorine, bromine, iodine and astatine. Halogens are diatomic, meaning they form molecules of 2 atoms. The formulae of the halogens are F2, Cl2, bridge 2, I2 and At2. All halogens have 7 electrons in their outer shell. They form halide ions by gaining one more electron to complete their outer shells. Fluorine is not allowed in school, so observations and experiments tend to only involve chlorine, bromine and iodine. Properties of the halogens. At room temperature 20 degrees Celsius, the physical state of the halogens changes as you go down the group. Chlorine is a pale yellow-green gas, bromine is a red-brown liquid and iodine is a gray-black solid. This demonstrates that the density of the halogens increases as you go down the group. The physical state of the halogens at room temperature. Reactivity of group 7 nonmetals increases as you go up the group. This is the opposite trend to that of group 1. Each outer shell contains 7 electrons, and when the halogen reacts, it will need to gain one outer electron to get a full outer shell of electrons. As you go up group 7, the number of shells of electrons decreases, period number decreases moving up the periodic table. This means that the outer electrons are closer to the nucleus, so there are stronger electrostatic forces of attraction, which help to attract the extra electron needed. This allows an electron to be attracted more readily, so the higher up the element is in group 7 then the more reactive it is. Diagram showing the electronic configuration of the first 3 elements in group 7. Exam tip. Solid iodine, iodine in solution and iodine vapor are different colors. Solid iodine is dark gray-black, iodine vapor is purple and aqueous iodine is brown. Predicting group 7 properties. You may be given information about some elements and asked to predict the properties of other elements. The information you might be given could be in relation to melting, boiling point or physical state, density, so it is useful to know the trends in properties going down the group. Melting and boiling point. The melting and boiling point of the halogens increases as you go down the group. Fluorine is at the top of group 7, so will have the lowest melting and boiling point. Astatine is at the bottom of group 7, so will have the highest melting and boiling point. Physical states. The halogens become denser as you go down the group. Fluorine is at the top of group 7, so will be a gas. Astatine is at the bottom of group 7, so will be a solid. Color. The color of the halogens becomes darker as you go down the group. Fluorine is at the top of group 7, so the color will be lighter, so fluorine is yellow. Astatine is at the bottom of group 7, so the color will be darker, so astatine is black. Exam tip. If you are doing the supplement extended course, you can be asked to identify trends in chemical or physical properties of the group 7 elements, given appropriate data. Firstly, make sure that you have placed the elements and associated data in either ascending or descending order according to their position in group 7. Then look for any general patterns in the data. Group 7 displacement reactions. A halogen displacement reaction occurs when a more reactive halogen displaces a less reactive halogen from an aqueous solution of its halide. The reactivity of group 7 nonmetals increases as you move up the group. Out of the 3 commonly used halogens, chlorine, bromine and iodine, chlorine is the most reactive and iodine is the least reactive. Color of halogens in aqueous solutions. Halogen displacement reactions. Chlorine and bromine. If you add chlorine solution to colorless potassium bromide solution, the solution becomes orange as bromine is formed. Chlorine is above bromine in group 7, so is more reactive. Chlorine will therefore displace bromine from an aqueous solution of the metal bromide. The least reactive halogen always ends up in the elemental form. Potassium bromide plus chlorine, right pointing arrow, potassium chloride plus bromine. 2K BrAq plus Cl2aq, right pointing arrow, 2KClAq plus bridge 2aq. Bromine and iodine. Bromine is above iodine in group 7, so is more reactive. Bromine will therefore displace iodine from an aqueous solution of metal iodide. The solution will turn brown as iodine is formed. Magnesium iodide plus bromine, right pointing arrow, magnesium bromide plus iodine. MgI2AQ plus bridge 2AQ, right pointing arrow, MgBr2AQ plus I2AQ. Summary table of displacement reactions. Exam tip. Iodine solid, solution and vapor are different colors. Solid iodine is dark gray-black, iodine vapor is purple, and aqueous iodine is brown. Transition elements. General properties of the transition elements. They are very hard and strong metals and are good conductors of heat and electricity. They have very high melting points and are highly dense metals. For example, the melting point of titanium is 1688 C, whereas potassium in group 1 melts at only 63.5 C, slightly warmer than the average cup of hot chocolate. The transition elements form colored compounds and often have more than one oxidation state, such as iron readily forming compounds of both Fe2+ and Fe3+. These colored compounds are responsible for the pigments in many paints and the colors of gemstones and rocks. Transition elements, as elements are in compounds, are often used as catalysts to improve the rate or reaction in industrial processes. Transition element catalysts of platinum or rhodium are also used in car exhausts in the catalytic converter to reduce the levels of nitrous oxides and carbon monoxide produced. The transition elements on the periodic table. Exam tip. Although scandium and zinc are in the transition element area of the periodic table, they are not considered transition elements as they do not form colored compounds and have only one oxidation state. Transition elements oxidation numbers. Extended. The transition elements have more than one oxidation number, as they can lose a different number of electrons, depending on the chemical environment they are in. For example, iron either lose 2 electrons to form Fe2+, so has an oxidation number of +2. Loses 3 electrons to form Fe3+, so has an oxidation number of +3. Compounds containing transition elements in different oxidation states will have different properties and colors. Ions of the same element can have different oxidation numbers forming different colors. Uses of the transition elements. The transition elements are used extensively as catalysts due to their ability to interchange between a range of oxidation states. This allows them to form complexes with reagents which can easily donate and accept electrons from other chemical species within a reaction system. They are used in medicine and surgical applications such as limb and joint replacement. Titanium is often used for this as it can bond with bones due to its high biocompatibility. They are also used to form colored compounds in dyes and paints, stained glass jewelry. Noble gases properties and electronic configuration. The noble gases. The noble gases are in group 8 or group 0. They are non-metals and have very low melting and boiling points. They are all monoatomic, colorless gases. The group 0 elements all have full outer shells. This electronic configuration is extremely stable, so these elements are unreactive and are inert. Electronic configurations of the noble gases. He, 2, Ne, 2, 8. Ar, 2, 8, 8. Ker, 2, 8, 18, 8. Z, 2, 8, 18, 18, 8. Noble gases are inert, unreactive, as they have a full outer shell of electrons, so do not easily lose or gain electrons.